Hello, and in this video we're going to look at graphs of polynomial functions. We're going to take a look at short run behavior, the intercepts vertical and horizontal x and y. We're going to look at how to find the horizontal intercepts by factoring, looking at its factored forms or using technology. We're going to see what happens at those horizontal intercepts, whether they're going to cross or touch. We're going to look at specifically at zeros that have multiple zeros, and we're going to look at how to look at an inequality, help us determine what the graph looks like. We're going to write some equations using the intercepts, and we're going to estimate extrema using Desmos. So those are the topics we'll go through in this section or this video. Let's start with what does a polynomial graph look like? So basically, we have a polynomial function where it has a constant x to some power, value power, and then you got some lower powers. So lower power functions, x to the n minus 1, and so on down to a constant value. The lead term, basically the highest power, determines what the polynomial function looks like. And this value of a is going to also help us in determining that look. Now, so the lead term, which is the highest power, is going to depend on, or it's going to affect it by whether it's going to either be even or odd powers. So even powered functions look one way and odd powered functions look another for the lead term. Okay, so even power functions either go up from on the right and left hand side, and there's some turns in here maybe, or they go down from either side. So they go down, meaning that they go down like this, and they might have some turns in them, and then they go down. So even power functions either go up or down depending and have something happening in the middle. Okay, if a is positive, then it's going to look like that. If a is negative, then it looks like this, with something happening in here. Something is going to turn, there's going to be some turns or something happening in the middle. It's possible. Okay, if we have an odd powered function, it's going to go this way and continue to go this way if it's a is positive, and there could be something happening in the middle. We don't know. There's something happening in the middle there. And if a is negative, then it's going to go down, have something happen in the middle, and then continue to go down. So what we're going to do is we're going to look at this short-term behavior here in between what's happening in the middle here to help us determine where it turns and what's going to happen there. But overall, the function's going to have something like this is going to happen if it's even, either up as it goes to infinity, and up as it goes to negative infinity, or down as it goes to negative infinity, or down as it goes to positive infinity. The odd functions continue to go up. They may go down a little bit in the middle, but they continue to go up overall, and they go down overall. So that's what the polynomial functions look like, and it depends on this lead term, and the graphs are going to look like these things here. So we're going to look at specifically some examples of those, and we'll see what happens here in the middle. Okay, so that short run behavior, that's the intercepts and stuff. They're going to tell us what's going to happen. We're going to be able to find them by factoring, like this one's factored. So we're going to be looking at this. And this one we're going to look at specifically single and double term factors. This is a double term factor right here because it has a square on it. So what we're going to be doing here is we're going to be looking at the horizontal intercepts. Now, the vertical intercept is a simple one. It would take into consideration all of the values and that are added and subtracted to each term. So in this case, this one doesn't have a value here, so that's going to be 0. So basically this has a vertical intercept at 0, 0. Because if I put 0 in here, I'm going to get 0 out. So its vertical intercept is 0, 0. It's also a horizontal intercept as well, but it's one vertical intercept because what's happening here is we're going to put 0 in there and figure out the whole vertical intercept. So if I put 0 in there, t equals 0, that gives me a c value, a c of 0 value of 0, which is my vertical intercept. Now the other intercepts, since they're in factored form here, we can just set this equal to 0 and look at the terms. Each term gives us a 0. So that one we've already done. That gave us 0, 0. This one, the t value is going to be 3. The t value is going to be 3 there. And so that value is going to be 3, 0. And this t is going to be a t that's going to equal -1. So that's going to be a -1, 0. So those are my horizontal intercepts. Okay, horizontal intercepts are the x-intercepts. Okay, so we have that. So we know what's happening here. We can figure out the exponent on this as well. This has a 1 exponent. This has a 1 exponent. This has a squared exponent. So this is really the same as a t to the 4th power as its family. So t to the 4th family. And so, and it's positive, because if we multiply this term and this term and this term, we get a positive value. So it's a positive t to the 4th value term. So what that's going to look like is it's going to look like this. It's going to go up on both sides because it's even and it's positive. We now know, if we're just drawing a sketch of this graph, we know that it goes through 0, 0, goes through 3, 0, and it goes through -1, 0. Now, we haven't talked about crossing and touching yet. So any odd-powered function, odd-powered term is going to cross as a 0. But any even-powered one is going to touch. It's going to bounce off. So this power right here, this 0 right here, is actually going to be a touching. So it's going to, the curve touches here. Okay? So it's going to touch at this point. So that means it has to come like this, because it's got to go that way, right? And it's going to touch, so it's going to come up. And if we were to put 0, so it has to come back down and cross at 0, 0. So it's going to go like this. It's going to come down and look like that. So I don't know what my y-axis, how high and low it goes, but it's got to look like this because it touches here, it crosses here, and it crosses here. And we know it happened, these both ends have to go up on this one. So it's going to look something like that. So we can specifically graph that on our graphing technology and find these points, the max and min points here. We know this minimum point is at a -1, 0 though, because we know it touches there, so that's given that it's a minimum point there. So we can figure that out. The other ones are going to be somewhere between -1 and 0. There's going to be a maximum, and between 0 and 3, there's going to be some kind of minimum. Because we know that in general it goes like this, upward, because of that family that we're dealing with here of graphs. Okay, so that's what that looks like. Okay, so now let's look at another example and see what happens in this type of problem. Let's see if we can do another example with another graph. So if we were to look at this function right here, f of x equals x to the x minus 3 to the third and x minus 2 to the second, we know here that that graph has, it's going to look like an x to the, this is x to the third here for this piece, and this is x to the second here, so that's going to be an x to the fifth graph, a fifth power graph. So, and we look at the lead terms here, that's going to be x and that's going to be x, so it's going to be a positive. So that means the graph is going to look something like this on the end. There might be something going in the middle and that's going to look like that because it's odd, so it's going to look like that. We know what the intercepts are. We can let's find the intercepts. So we can put 0 in there. If we put 0 in there for the vertical intercept, put 0 in there, then this is going to be negative 3 cubed, and this is going to be negative 2 squared, and that's going to be our intercept. And in this case, that's going to be negative 27 times 4. Okay, so that's 108, negative 108. So negative 108 is our vertical intercept. So it's going to cross there. Now, we also know that when we set this equal to 0, x minus 3 cubed and x minus 2 squared, we're going to get 2 additional horizontal intercepts. So we get x minus 3 equals 0. That's going to be x equals 3. It's going to cross there because the power is odd, or it equals 3 here. We're going to have x minus 2 equals 0. So x equals 2. It's going to touch there because the power on that one is an even number, or 2 on that one. So an even number power up here is going to just make the crossing at a 2 just touch. So in general, the graph, okay, we're going to cross way down here at 108, negative 108 on that graph. It's going to cross at 2 and 3. 1, 2, 3. So it's going to cross, or it's going to touch there, and it's going to cross there. Okay, we know it's going to go up. Okay, so it's got to come up through 3 and then touch here. So it's going to come up through here, touch there, turn, and go up. So the graph is going to look something like this. It's got to go up, touch, turn, cross, and then go up. Something like that. Okay? It's an x to the fifth power. So it's got to go like up, continue to go up because it's positive. All right, so we know that's kind of what it looks like. All right, so we can kind of sketch the graph of that, knowing those 3 points and knowing what it looks like on the ends. As x goes to infinity here, the function is going to go to infinity because it's going up. As x goes to negative infinity, the function is going to go downward, goes that way, so it's going to go to negative infinity here. So that's our long run behavior on this function. And then we have a maximum. We can say here there's a maximum at 2, 0, and then there's some kind of minimum between 2 and 3. We would have to use our Desmos to figure that out. Because there's no factoring this, there's nothing we can do to find that answer. Okay, so let's look at the next thing. Solving the inequality to help you graph it. So looking at this one specifically, let's go through the same process as we did before. Okay, so if we were doing this, each one of these has a single power. So that means all of the zeros, or horizontal ones, are going to be crossing. They're not going to be touching. There aren't any even powers on each one of these. We know that this is x, this is x, this is x, so this is x to the third family. We know it's -2 in front, so that's a negative. Negative. So that means it's going to look like, it's not going to go up, it's going to go down. It's going to look like this. Something happened in the middle, goes down. So it looks like this. We have to figure out what happens in the middle. All right, because if we multiply -2 times x times x times x, that's going to be -2x cubed. That's going to be our lead term. That's going to tell us where that it's going to look like that. Okay, so if we plug in our 0 to find our vertical intercept, so we're going to put in 0 for x. Okay, so that's going to be -2 times, this is going to be -2. This is going to be 0 plus 3 or 3, and then 0 plus 1 is 1. So if we do that, that gives us our answer for this. So that's 4 times 3, that's 12, times 1, which is 12 again. So our vertical intercept is going to be 0, 12. We know that our horizontal ones are going to happen at 2. So x minus 2 equals 0. That's x equals 2. Or 2, 0. Our next one is x plus 3 equals 0. So x is going to be -3. That's going to be -3, 0. And x plus 1 equals 0. So x is going to be -1. So -1, 0. So we know those are our horizontal crossings. We know it goes down because of the -2. We know the vertical one, so we kind of have a graph or an idea of what the graph looks like. Okay, so we know it crosses at 12 up here, 0, 12. We know it crosses at 2, 2. We know it crosses at -3. We know it crosses at -1. So we know all of those points that it crosses, and we know that it has to come down first. It's a negative, so it has to come down first, turn, come back up, go up here. I don't know where it turns somewhere in here. So if we look at this, there's 3 here, it'll probably turn after this one. So we know it kind of comes down, maybe turns somewhere in between here, goes up, crosses here, turns maybe, goes down through there. So it looks like that. Okay, we would have to graph it on Desmos to figure out where it actually turned. Okay, but it would turn somewhere in between each one. Okay. Now, if we wanted to just check to see if we were right here, we can check the inequalities here to see if we're in the right range. Now, we're going to use this inequality method to help us find a domain of a function. And so let's do that as our next example. So we could check to make sure that this is negative after 2 by plugging in 3 to the function and figuring out what it is, right? So we could plug 3 in here and make sure that 3 gives us a negative value, right? 3 is a positive here, 3 is a positive here, 3 is a positive here. So 3 positives times -2 is going to be a negative value. So we can then check, we can say, oh, okay, 3 is a negative value, it's down here below the function. We should be able to put in 1 and get a positive value. So if we put 1 in there, 1 is going to be a negative value, positive value, positive value. So positive times negative is a positive answer. So we don't really need to know what that answer is, but we can then say, oh yes, up here it's going to be some positive number. It's above the axis. So it's decreasing there because we know it was a positive, it went through 0, and then it's a negative answer. So that's what an inequality would do. You could check your thing to see if they're positive or negative. Okay, so let's do one of those examples for a domain problem. So we're going to find the domain of this problem. Okay. Here's my example. Find the domain of f of x equals square root of 2 plus 7x plus 3x squared. So we're going to find the domain. So that means that 2 plus 7x plus 3x squared has to be greater than or equal to 0, because we can't take the square root of a negative number. So what we would then do here is I would take this and I would try to factor it to find the zeros, because we want to know when it's greater than or equal to 0. Okay, so I'd want to find out where it is 0 first. So 2 and 1 give us 2, and 3x and x gives us 3x squared. We need to get 7. So that's checking the FOIL here. That's 2 and 3. That's 5. That's not right. So I need to change the positions. So this has to go here. And I check this. 6 and 7. That works. So this is my factored form of this. This is x and this is 6x. That gives us a 7x in the middle. So I just factored it. Looking at what I needed to do here, I needed 2 and 1 to give me 2, and I needed 3x and x to give me 3x squared. I didn't have any other choices, so it's pretty much easy. I just rearranged the 3 and the 1 on the x to make sure I got 7x in the middle. Okay, so if we're saying that this has to be greater than or equal to 0, that means both of them are going to be positive, or both of them are going to be negative. Okay, so that's what we need to test. But we can just easily test this by just finding the zeros first and then checking on either side. So what we're saying here is 2 plus x is equal to 0 at x equals negative 2. All right, and then 1 plus 3x equals 0 at x equals negative 1/3, because you move 1 over, divide by 3. That's what you get. So basically what it's saying here is that we, on a number line, we have two places where it's 0. It's 0 at negative 2, and it's 0 at negative 1/3. Okay, so what we need to do is we need to check in between to see what they are, what happens to the function then. So I'm going to try some other values for x that are on either side. So let's try some values on, let's try something in this interval here, because we need to know whether it's going to be positive or negative, so that we can then determine whether it's part of the domain. So I'm just going to use negative 3 because that's definitely in this interval. I'm going to plug in negative 3 into the function. So I'm going to plug it into 2 plus x and 1 plus 3x. That's our function. I don't need to worry about the square root, and I only need to know whether it's positive or negative. It's because I just need to know whether I can take the square root or not. So if I put negative 3 in here, I'm going to get a negative number, right? Negative 1. If I put a negative 3 in here, I'm going to get a negative number, right? So negative 3, that's negative 9. It's going to be negative 8 and negative 1. That's going to give me two negatives multiplied together, so I get a positive solution here. So it's going to be positive on this side. We're going to break right here where it's 0, but it's positive on that side. That means that's part of my domain because I can take the square root of a positive. Now I'm going to break right here. Now, as you can see here, there's a number right here that was negative 1. I'm going to test that one out next to see what happens in here, in this little region right here. So to do that, I'm going to put in negative 1. Negative 1 is positive here, right? So you get 1 out of it. And negative 1 here is negative 3 plus 1. That's going to be negative 2. Negative 2 and times negative 1, that's a negative number. So this is negative in here. So that's not going to be part of our domain because we can't take the square root of a negative number. All right, and then 0 is on this side, so I'm going to plug 0 in here. That's positive, so we get a positive value here. Plugging in 0. So I tried 0, 1, -1, and -3 in this function to see whether I got a positive or negative number, because I just need to know whether it's positive or not. So this is going to tell me what my domain is. It's going to be in this interval, including this number, because that number is 0 and we can have it equal to that number. So my interval here is going to go negative infinity to 2, -2, including, and it's going to go from -1/3, including, to infinity. So that's my domain for this function, because I've checked positive and negative in those regions. I found out where it was 0, and then I checked in between to make sure that I can get in which area is going to give me the domain of this function. Okay, so that's how we use intervals to check domain and to help us graph. All right, writing equations using intercepts. So if we know some of the intercepts, like for example, we know the degree is equal to 4, and we have x equals 4 as a root with a multiplicity of 2. Now multiplicity means that you have 2 of those roots, so this is going to be x minus 4 and x minus 4. Because you have a multiplicity of 2, you're going to use that twice. And then x minus 1 and x minus 2, or x equals 1 and x equals -2 is that, and we have a vertical intercept of 0, -3. Okay, so what we have here is when we have a degree and we know the roots, we know 4 roots here, 1, 2, 3, 4. We know that it looks like this, x minus 1 for this root, x plus 2 for this root, and then the 2x minus 4s for the 4 root with multiplicity 2. Now, this function can be anything because we don't know how it's stretched. We don't know this a value. Now, this intercept is going to give us this a value. We're going to plug this number in and figure out how it's stretched and which way it goes, because it's going to tell us. This is going to tell us. So we have a general function just knowing the horizontal roots, but we don't know a specific one until we're given an extra point that's not a horizontal root. Now this vertical intercept is not a horizontal root, or 0, so it'll help us find this value of a. So what we do is we just plug that in. So plugging this in, this is going to be -3 from the point. A is what we're trying to find in. We're plugging in 0 to each one of these. Okay, and this is going to be -1 times 2 times -4 times -4. And that's going to be multiplied by a, and then we're going to divide that number into 3. So in this case, we have -6, or we have a negative number. So it's negative because there's 3 negatives. This is 16. 4 times 4. 16 times 2 is 32. So we're going to have -32a equals -3. So a is going to be 3 over 32. They're both negative, so it's a positive. So our function here is going to be 3 over 32 times x minus 1 times x plus 2 times x minus 4, and we can shorten that up by putting a square on it. So this is our function that relates to that. Now if we wanted to know the actual polynomial function, we would have to multiply all of this out. and then multiply it by negative or 3 over 32. And that's how that would be found. Now, we can, in the last part of this, finding extrema, what we would want to do is use Desmos. Okay, so once we have our normal graph here, we would want to plug this into Desmos, and it would tell us what our extrema values are. So we know this is x to the third power. We know it's negative because of the negative 3 times x, negative 3x times x times x. We know the intercepts are 0, 0, because we have a single term here. This one is going to be negative 2, 0, and this one's going to be 4, 0. Okay, so it's going to look something like this. It's going to go right here, negative 2 and 4. Okay, now we know it's negative, so it has to go down. So it's going to come through here, cuts right here, come through there, and go down. So the graph is going to look something like this. Okay. Now, what we would want to do to find the extrema values, we know that there's a minimum and a maximum. We would take this and we would plug it into our graph. Okay, so here's our graph. We type this in. It's negative 3x. Y equals negative 3x. X plus 2 and minus 4 plus x plus 2 x minus 4. Okay, and we look at the graph. We zoom out because we can't see the max and minimum points. It's really pretty high, actually. And we look at this. I will want to change this. Let's change it to the x doesn't have to go to negative 160, so negative 10 to 10. Okay. All right. So we can look at this. There's our maximum, there's our minimum. Okay, so we would write those down as our maximum and minimum points. We can just click on it, it would tell us what they are. Okay, so Desmos would give us the max and min, and in this case they're very high, so this axis would be labeled quite large values because those are quite large values on the y and the x, or the y values. Okay, all right, let's look at one more thing here. Lastly, so we're going to look at a graph and then try to determine what the equation is. So if I have a graph, let's say this is my graph. It's important, and we're going to write an equation from it. So my graph's going to come down. It's going to have go down like this, come through here like this, go down and turn like that, and go down. Okay. So these points are going to be, this point's going to be negative 2. This one's going to be negative 1. This point here is going to be 4. And this point here is going to be 4. Okay, so if we look at this, this is an odd function. Okay, it's an odd function because it goes down in general. There's this thing in the middle where it goes up a little bit, but it's coming down. It's coming down, it's going down. So it's a function like x to the third, it's x to the third, x to the fifth, x to the seventh. It's one of those functions. If we look at this, there are 1, 2, 3 crossing points. Okay, 3 crossing points. So the problem here is this crossing point is kind of bent. And when it's bent like this, it has a little, this is a triple root because it's bent like this. This just crosses through straight. If it crosses through straight, it's a single root. So this bent thing right here is meaning it's a triple root. That means this x minus 4 that we would have for this root would have to be cubed. All right, this one here, this x plus 1, that's to the first power. This x plus 2 is to the first power. So we got 1, 2, and 3, that's 5. So it's an x to the 5th power is what it is. Okay, now if this just went straight through and didn't bend like this, then it would be x to the 3rd power. But it has this little bend in here. So that little bend is going to cause this to be a triple root. So you need to be careful of that. If it just touches, it's a double root. And we did that earlier, but I wanted to show you this triple root and what it looks like. So in this case, you got to watch out for that. Okay, so that means my function is some value we don't know, x plus 2, x plus 1, and x minus 4 to the 3rd power. Now what we would then do is we would take that y-intercept that they gave us of 4 and plug it in here to figure out what a is. So we have the point 0, 4. That's this y-intercept, or our vertical intercept. We would stick that in here. 4 equals a times 0 plus 2, 0 plus 1, 0 minus 4 cubed. Okay, and we'd figure this out. So this is 2 times 1, that's 2 there. So this part's 2. This is negative 4 to the 3rd power, so that's going to be negative 64. Okay, and a times that equals 4. So this is going to be negative 128. A equals 4. So we're going to take this and we divide. So it's 4 over negative 128 equals a. That reduces. 4 goes into 128 32 times. So that's going to be our a value. So our function here for this is negative 1 over 32, x plus 2, x plus 1, x minus 4 to the 3rd power. That's our function for this graph. Now if we multiply it all out, we get a long polynomial function with x to the 5ths, x to the 4ths, x to the 3rds, x squareds, x's, and constants. Okay, so that's what's going to happen here in this section of polynomial graphs.